noticed or not, but in the review section online, where it says review for final exam, I put a list of topics. So the list looks like this. It's 2 pages long, 44 points that I wrote, okay? And so what I did is I went through the class list and made up 44 items that would be good for test material. I didn't ask all of them. Obviously, that would be really, really long, final exam. But what I did then, after I made this list, is then I went and made the final exam by going through this list. Okay, so I said, oh, that would be a good test question. Oh, that would be, right? And then I deleted a few because it was too long. And the final form is, 11 pages, regular size paper. I think 6 questions in all with multiple parts, right? So a little bit of everything. So you really need to practice everything. And the best approach for practicing for the final exam would be go back through the class notes and write down questions. So you look at what questions I did in class and write those down on a separate piece of paper as a practice question. And then you'll have practice questions on everything, but that will also have made you review everything as you did that. Right? So you take the time, you write down all the questions or a little bit of everything as just a question with no solutions. So you've made up a study sheet. And then once you're done going through all the lectures, making up questions, you shut that all down, put your notes away, and then try all the questions without looking. Right? So you've reviewed them, you've done your tests, and then you can put little stars by things you didn't remember. And the solutions to all of them are done out in the notes, so you can always go back and see exactly how it was supposed to be done and check your own work by going back through them again. Okay, so that is really my advice for that. I didn't print this list of topics out for you, but we're just going to go through it and talk about each item. Okay, that's what we're going to do today. Okay, so is that in focus? I think so. So the first thing I put on here is addition is the diagonal of the parallelogram. What does that mean? So we're talking about vectors here. So if you have 2 vectors, u and v, when you add them, u plus v gives you that diagonal of the parallelogram. So here is v and u, and adding them gives you the diagonal. And what does subtraction give? Do you remember? And which way does it point? Because that's important. What's that?
Oh, you take the v and
yeah, so if you go u minus v goes this way, right? So it gives you that vector, and if you move that over here, u minus v, it gives it forms a triangle. So it gives the third side of the triangle. In that direction. Okay, so third thing is the length. So the length is the square root of the dot product, right, for whatever size. If it was a 2 by 2, it's a squared plus b squared. If it's a 3 by 3, it's a squared plus b squared plus c squared, and so on. It's the square root of the dot product. Now, on test 1, we had something like this. Find the length of 2u minus v. So what some people did in error is break this up to be like 2 times the length of u minus the length of v. You can't do that. You need to calculate this first, and then do the length. You cannot do this. Okay? It's, quite a few people did something like that, like pulling a number out of the length. You can't, if you want the length of something, you need to keep it together, find that vector, and then do the length. Or the dot product or anything. You need to do it first and then the answer. Number 4, I put parallel vectors are scalar multiples. So what does that mean? So if you were looking at 2 vectors to know if they're parallel, how do you know? So if we have 1, 2, 3, what would be a vector that's parallel to that?
2, 3, 4.
Right. Oh, not equals. So 2, oh, not 2, 3, 4. No. 2, 4, 6. Right, because it's a multiple. What would another one be? If we multiplied by, say, -3, -3, -6, -9. So those are parallel vectors. They can be in the same direction or the opposite direction. But if they're a scalar multiple, they're considered parallel. What if we were to take the cross product of 2 vectors that are parallel? What would that give us? So remember the cross product.
Give us the normal.
No. Okay, so I'm not going to do the cross product. You can review how to do the cross product, but so think determinant, that's more recent, right? What if a determinant, you were finding the determinant of something that had 2 rows the same, or a multiple of each other? What's a determinant, do you remember? 0. A cross product is actually just a determinant. It's actually the Laplace expansion along row 1. That's what the cross product is. It's the exact same thing. This is plus minus plus. And you do, well, I guess I'll do it. So I is plus, and then you cross these off, remember? And you write down 2, 3, 4, 6, and then you do the determinant of that. And then you say minus j, and you cross those off. So 1, 3, 2, 6, plus k, cross those off, 1, 2, 2, 4. So when you do this, what do we get? 12 minus 12. Here, 6 minus 6, 4 minus 4. Okay, so back to my original question, the cross product of parallel vectors are what? 0, gives a 0. So, that being said, cross product gives a vector as an answer. And the dot product gives what? Does it give a vector? No, a scalar, or a number. And what do we know about the dot product? What do we use it for usually? So the dot product gives a number as the answer. What does that number tell us about the two vectors that we took the dot product of?
If they're perpendicular or not?
Mm-hmm. And what if they're negative or positive? That also tells us something. You may not remember. Yeah, so if the dot product is...
Positive, it's acute.
It's acute, right? Or less than 90 degrees. And here, when we are talking about the angle between vectors, it's in degrees. Later, when we're doing polar form, it's in radians. Okay? So here we're doing degrees, and on the test I actually wrote in degrees for this one, but polar form I didn't mention radians. Polar form's always in radians. Okay? Dot product minus is obtuse, which is greater than 90 degrees, and the dot product equals 0. It's perpendicular. Perpendicular or orthogonal, which is 90 degrees. Okay, so like I said, it's in degrees here. There was a formula for the angle between vectors. So you need to know that. You need to memorize it. So you would do cos theta is u dot v over the length of u and the length of v, which of course, if the dot product was 0, you wouldn't have to do anything because you'd say 90 degrees. But if it's otherwise, then what do you do on your calculator to solve this? Yeah, cos inverse or arc cos of whatever that number is. Now, where some people go wrong with this is if they round off this number, like they do it as a fraction, they round it off to 2 decimals, it's not going to be accurate. You need to either save that number or type the fraction in as the best. So if you had, like, say, 1 over 7 here, say this worked out to be 1 over the square root of 70. Okay, so you have cos theta equals 1 over the square root of 70. So when you find theta, you'll do cos inverse. So you could put this number in your calculator and get a decimal. But as soon as you do that and round it off, the answer, the next step's not going to be accurate to 2 decimals, which is what I want. So I would suggest you either write down everything you see on the screen to keep it accurate, or just type in the fraction here when you do it. So I'm in radians now, so I'd say, okay, well, I need to be in degrees. So I switch to degrees, so figure out how to do that on your calculator. Then I would hit on mine, on top of the cos button. No, you probably can't see it there, but you can see that there's orange. So there's the cos button. I have to hit second function cos. And then I would put a bracket and put the 1 divided by square root of 70 right in a bracket. That's how I would do it. And then it would be 83.13 or 14 degrees. Okay. So if you just do, say, 1 over root 70 by itself, and then you write down like 0.12 and then do cos inverse of 0.12, it's not going to give you the accurate answer. 83.11 instead of 83.13. Okay, and I want it you have to be accurate in math, so accurate to 2 decimals. So if you kept more decimals, it would work out okay, but it's best just to leave the fraction. So you need to memorize that. And of course, how to do the dot product and the cross product. So on the list, I also talk about linear combinations. Now, in Chapter 1, we introduced linear combinations, but we went back to it in Chapter 2, and that's where I would look at it, is in Chapter 2. Because in Chapter 1, we hadn't... Okay, so in Chapter 1, we had not learned how to solve a system using row reduction. So it was really sort of awkward to try to solve a linear combination in Chapter 1, but it was first introduced there. And we did 2x2s and a few 3x3s, but only by looking at the actual vectors and trying to figure it out, the pattern. So a linear combination is when you have vectors, doesn't matter with the size. I'll just put V1, Vn, and so on. Doesn't matter how many. So they can be any size. We mostly work in R2 and R3, but... Okay, so this is itself a linear combination. So when I first introduced linear combinations, if you were to go and listen to the lecture again, I said asking for the linear combinations is the same as saying what's the range, or like what are the answers you can get. So when you put these vectors together, what kind of answers can you get? And then I said that's called the span, is the general form for the vectors. So we use this for 2 different things, linear combinations. It's just a system of equations, but we can do 2 types of questions here. One is talking about the span. So let's say, for example, a question could be like on the test, find the span of the vectors you could have 2 or 3 vectors, it doesn't matter. Do you see what the pattern is without doing anything? Or could you maybe guess what the pattern is?
1 plus 1 equals 2, 3 plus 0.
Yeah. So, but how you'd actually find it, sometimes you can't just see the pattern. So this pattern is that I put 2 down, so add another one, 1, -5, so what would go here? I put 2 numbers down, and for the 3rd number, I added them. So this would be -4. Right, so those all fit the same pattern. But say you didn't see the pattern, how you solve it is this. You set up the linear combination. And the span is saying, what kind of answers can I get if I were to put different values of A, B, C in here? What are all the types of answers that we can get? And in Chapter 1, I said, I'm going to always make them so that you can try to figure them out, like we just did. But in Chapter 2, I said, well, you don't need to worry about trying to figure them out on your own. You can actually just row reduce and get the answer. So, to solve a system, you could row reduce this. Okay, so you're going to do row reductions. If you're not really, really good at row reductions yet, then you should make sure you try to figure that out. So go back to the lecture. When we row reduce this one, okay, I'm not going to do it through, but this is what we would end up with in the last row. Okay, I'm not sure what the numbers would be in the other two rows, but this is what we would end up with, okay? Which is what you're looking for to happen, is to get some kind of condition at the bottom. So we talked a lot about what happens when you row reduce and the types of solutions you can get. So if there's a row of zeros, then it's consistent, or it has an answer. But if it's zeros and then a number here after the equals, then it's no solution. So we want to know where the solutions are. So we say this is a condition. So z minus x minus y equals 0 has to be true for this to work. So z has to equal x plus y. You could solve for any letter, like you could solve for x and then put that in the x. I solve for z, so when I rewrite this vector up here, I solved for z, so I'm going to rewrite that vector and put that in for the z. Okay? So, and in my solutions, I would often write this way, in vector form, 0, 1, 1. If you went on and took another linear algebra course, they would ask you to find what's called a basis, which is a set of vectors that are more simplified, that span the same space, and these are the vectors right there. So just, if you go on in math or ever use this anywhere else, do you see what I did here? I took the x out, and where was there an x? Here, 1, no x's, and 1x. And then the y's. So those two vectors are called a basis. Okay, so that's span. And then the second type of question that we could be asked, that you sort of set it up as a linear combination, is whether the vectors are dependent or independent. So if we had the same vectors and we were asked for whether it's dependent or independent, we still set it up as a system. Good thing I'm not scared of bugs. Oh, a little scared. I didn't think it would jump. See it?
Yeah.
Who wants it? It's like a beetle. Hope you guys aren't scared. Now you're all going to be watching it. Someone can step on it, but I'm not going to kill it. So you guys can step on it. Okay, so the difference is, if you're going to set up the span, you put x, y, z, because you're trying to find what vectors will work. And dependent and independent, you're just trying to solve for equals 0. And it's dependent if what? Basically, if you get a free variable, or if it's infinitely many solutions. And it's independent if it has one solution. So we only have one A, B, C that will work, and that is that A is 0, B is 0, and C is 0. Now, if you've already done the span, this part is really easy, because don't do dependent, independent first and then try to find the span. Always go, if you have to find both, always span first and then this. Because if you put zeros in and row reduce, and then try to put your x, y, z, you have to do the row reduction all over again to get your condition. But if you start with x, y, z here, then you can replace those x, y, and z with 0. So up here, if we were row reducing, our last line would end up looking like 0, because if we put x, y, and z all as zeros, then we just have a 0 here. And this would have infinitely many solutions. I don't know what they are, but it will have a free variable if there's a row of zeros, so it would be dependent. What would it have to look like when you row reduce to be independent? Right, because that would be a lead 1 for the x, a lead 1 for the y, and a lead 1 for the z. This has no free variables. So when you go to find the solution, you have A equals 0, B equals 0, and C equals 0, which is independent. And I did a whole class on that, a whole lecture on that, and extra at the end of chapter 2 on that again. Okay, so if you, that's probably the most confusing part for a lot of people in the course, so you could go back and look at those. All right. Unit vectors. What does that mean to be a unit vector?
Vector of length 1.
Right. So we could be asked questions to find a unit vector. So vector of length 1 in the direction of a vector that's given. So there was a way to do that. What else could I ask? What about in the opposite direction? So what do we do different for that one? Yeah, just minus. So a unit vector is equal to 1 over the length of whatever your vector is times that vector. So vector u, whatever it is. Now if we wanted this would be in the direction. One over the length, and what would be the opposite direction? Minus. Now we also did, when you find that, those notes, we also did find a vector of length 5 or something, so I'll put a number there, right, but anything. Find a vector of length 2, find a vector of length 20 in the direction or opposite direction of a vector. How would you do that? How does that change this? Find the unit vector multiplied by 5. Exactly. Right, so once you find a vector of length 1, if you multiply it by 5, it's now length 5. All right, so that would be the other type of question. So there's that. The next topic I wrote here, it says, show that a triangle with given vertices is a right-angled triangle. How would you do that? Mhm. All right, so if you have 3, now why I put this down as a question, I mean, it's a legitimate question, but if you were given 3 points, and you want to find out or show that this is a right angle triangle, for example, what would the steps be? So I know dot product tells you if something's a 90-degree angle, but what do you take the dot product of?
The vector between the points.
Right. So a lot of you will just take the dot products of the points, but you actually need to do dot products of vectors, not of points. These are points. So your first step would actually be to what? Find the vector AB, the vector AC, and the vector BC, in any order, BA or, right? Then you do the dot products. Do you see what I'm saying? So be very careful of that. People always make a mistake. I did say in class too, be careful of whether I'm giving you something called points or vectors, because if you need vectors, you have to subtract the points first. And if I already give you vectors, those are not points. Okay, and I make sure I say whether these are points or vectors in the question, but don't ignore the words around what I write, right? So I might say with the vector U through point A. Okay, so you just have to be careful of that, because these points are sometimes written so they look like vectors. Right, so just watch the wording, that whether it's a point or a vector. Yeah, and then you would do dot products. I just put to find angles, but if you're trying to show that it's a right angle triangle, you don't actually need to find the actual angle. You just find whether there's one that's 0. Okay, so back to cross product. Someone mentioned this before. So earlier I said the cross product of 2 parallel vectors gives 0. That was one thing we looked at with cross product. So when we're talking about a plane, this is what came up. So the cross product is a vector, because it gives a vector when you do the cross product, that is perpendicular to both vectors. So forgetting about the parallel thing, because if 2 vectors are parallel, there's no, the dot product is 0. Or the cross product is 0 if they're parallel vectors. But if you've got 2 vectors, U and V, then, so, language. Vectors, 2 vectors, span a plane. Okay, so when you have 2 vectors, when I say it spans a plane, that makes it all the combinations of these 2 vectors, when you go longer and shorter, all the parallel vectors, or adding the 2 vectors together, or subtracting the 2 vectors. If you took all of the vectors that you could get using these as your guides, subtracting them the opposite way, adding them, going the opposite way. If I took every single one of these vectors, they make up a plane. So the span of 2 vectors makes up a plane, like a whole piece of paper. They're all flat on that. None of them go out of the paper. Okay? So if you took all the linear combinations of these, adding them together, multiplying them by 2, every possible combination, it makes up an entire plane. So every time you do something, you laid it out as a toothpick, it would be like a big sheet of paper, right? That would be what it would look like. The cross product of any two vectors isn't in the plane. It's perpendicular to the plane. So if here's a plane, and say U and V are right here, they make up this plane, then the normal vector is U cross V, is the vector U cross V, and it is perpendicular to the plane. Now, people got this wrong on test 2. I forget what the exact question was I asked, but it was something about, is the line perpendicular to the plane? Okay, and it was something like this. So say we have a plane. Let's just make up a plane. 2x plus 3y plus 4z equals 0. Okay, so here's the plane. What's the normal vector of this plane? 2, 3, 4. And here's the line. Okay. It's a bit different than the question on test 2, but similar, okay? So my question is the line perpendicular to the plane? The answer is yes. So here's our vector n. This is not on the plane. So if we were to draw this plane, here's our plane, and vector n is perpendicular to it. And why would this one also be perpendicular? This is the direction. And is the direction the same? Yeah, because remember, any multiple is the same, it's just longer. So the direction, 2 times 2, 3, 4 is 4, 6, 8. Right, so these two vectors are parallel. So if you think of parallel in being our normal sense, this one is just twice as long, right? So think of a vector that's parallel to that, but twice as long. There it is. So my question is the line perpendicular to the plane? Yeah, because it's the same direction as the normal, and the normal is perpendicular to the plane. Yes, the line is perpendicular to the plane, since it is parallel to the normal, and the normal is perpendicular to the plane. Right, so since it's in either the same or opposite direction, it's parallel to the normal, and the normal is perpendicular to the plane, so it's also perpendicular to the plane. Does that make sense? So what if I said, is the line parallel to the plane? With the exact same reasoning, you would say no, because it's in the same direction as the normal, and the normal is perpendicular to the plane, so it's not parallel, it's perpendicular. Now, where do people go wrong with this? Is that they take these two, and they do the dot product of them, and say it's not 0. But you're not trying to find if the normal and the line are perpendicular, because the normal is already perpendicular. So it would actually be the cross product if you show that these are parallel, but you don't need to do the cross product if you can see. The cross product tells you that that vectors are parallel. If you do the cross product, it's 0. But you don't ever need to do that, because you just look at them and you can see if they're parallel if they're multiple of each other, right? Okay. So how do you find an equation of a plane? So an equation of a plane has to have a point and two vectors. And in that class that I did this, I did all the possible scenarios, which are these. So you'll want to look up how to do them. You could be given 3 points. You don't just put the 3 points here. You need to find two vectors out of the 3 points and then use one of the points. You could be given two vectors and a point, in which case you just write it out because you've already got the two vectors and a point. Or 3, you could be given an equation of a plane in standard form. So this would be the hardest one. How would you find the vector form if you were given the standard form?
Find 3/4.
Yeah, exactly. You actually go back through this way. Find 3 points, take the 3 points, use them to get two vectors, and now you've got a point and two vectors, and then plug it in. Right, so they all sort of are the same. This would be the hardest. Not given any points, but given an actual plane. And you could do the opposite direction. So this is vector form. What if you wanted to find standard form? So you start with the equation of a plane, and what do we plug into that? So you could be given, the easy one would be to be given the normal and 1 point. The normal is ABC, and 1 point is your x1, y1, z1. So you just plug it in. That would be the easy one. What else could you be given? You could be given two vectors and a point. So how would you use or do this if you were given two vectors? So the point's good. That's your xy, x1, y1, z1. So that would be okay. But how would you find your ABC if you're given just two vectors? Cross product. So what would be another option? 3 points. So if you're given 3 points, you would use the 3 points to get two vectors. Then you would use the two vectors to get the normal, right? So that would be your options.
What comes so by 2 points?
2 points make a line, not a plane. So you could only do a line, not a plane. Yeah, but that could be lots of A, B, and C would work with that. Right? So, yeah, because it would be, yeah, it would just define a line instead of it wouldn't give it normal, it would give lots of possible points on a line, yeah. Yeah, so a line, so a line in R3 is just a smaller version. You just need 2 points instead of 3, or one vector and a point. 2 points. You would use one of the points here and subtract them to find the vector here. Or you could be given a vector and a point. And then you would just fill it in. So there's nothing more to it than that. Okay, so we are going to pause that.